Okay, Jim, go ahead.
Okay, since Shikai has introduced these topics before, so today I'm just gonna briefly introduce some famous diffusion models, which are very popular recently. And here is a timeline for these models. Here I categorize them into two categories, which is conducted in the original space and the latent space, and the two separate like development lines, like which is the first one is inspired by the statistical thermodynamics, and the second one is based on the score matching method. First of all, let's review a very simple generative model, which here we have the prior probability over xt and the observation x0, and the conditional probability is the probability of x0 conditioning on xt. Because the intuition of the denoising diffusion probability model is kind of an inverse process that could be really confusing if we didn't clarify the simple generative model first. So let's get into the denoising diffusion probability model, which is inspired by the statistical thermodynamics. The intuition is to here we use the same notation as in the previous slides. X0 is the observed images, and xt is the latent variable, and have a standard normal distribution prior. Here the intuition is to slowly from the right-hand side to the left-hand side, is slowly and systematically destroy the data structure by adding a small noise on the previous time points. And and it is defined by it is formulated by a Markov chain, and the transition probability it is denoted as q xt over conditioning on xt minus 1. Actually, from the right to the left, it should be the posterior distribution in the generative model, and from the left to the right should be the prior distribution in the generative model. But in this but in the DDPM, we defined the explicit form of the posterior distribution, and the prior distribution is approximated. Do you guys have any questions here about how the generative distribution is formulated?
What's the definition of a prior?
Actually, here the marginal distribution of the x0 is approximated. Actually, it's not a prior. It's just I mean the construction, the generative, because the form of the posterior is explicitly formulated, so the reverse process, I just call it a prior. So actually, the prior should be quoted here. It's not exactly the prior of the xt.
Okay. Yeah, so the forward procedure is you call it um you call it yeah
The forward process is the diffusion forward process, but it defines the posterior of the generative model. And the reverse time process should be the generative process in the generative model.
yeah. That's why you
It
draw the arrow in
approximates.
the you draw the arrows in a like in a in the right way, and then you call it reverse process.
Yes.
This is a figure from the DDPM model, or you draw
Yeah,
it
it's a
yourself?
figure from DDPM model.
Okay, okay.
And here, because we why the reverse process is approximated is that we don't know the exact distribution of the x0, so we cannot integrate out the x0. So we must use some approximation to approximate the reverse process. Here is the transition from the xt to the xt minus 1. And since the forward process is defined is formulated in a Gaussian distribution form, so the reverse process is also use some Gaussian distributions to approximate the reverse transition. And here some good properties can be utilized to assist the to help formulate the reverse process Gaussian distributions. Here, given the forward process, we can get the marginal conditional distribution on at each time point, which is also a Gaussian distribution. You can treat this xt as a noisy version of the observed random variables, and for even if we cannot have a explicit formulation or a closed form formulation of the conditional distribution of xt minus 1 conditional on xt, but by adding extra condition of x0, we can have a closed form formulation of the distribution, which is also a Gaussian distribution.
But how is beta tilde beta t is derived? I mean the reverse process.
Oh, you mean this one, right?
No, I mean qxt minus 1 given xt and x0.
You mean here, right?
Yeah, you got this one, right? How does this how is this derived?
Just to use the base rules to you can get such
Okay.
Such closed form formulation.
Okay, if you can get this, why do we learn some reverse model? Looks like you
yeah, that's a good question, because our goal is to generate x0 from xt, right? But if we already know that this distribution is conditioning on x0, if we already know the x0, we wouldn't need to solve this problem. So here they just use some approximation of the x0, which is made at time t. So here is because of this form, the x0 is approximate by this term here. where the noise term is approximated by some neural networks.
Oh, but do they still preserve the beta?
Yeah. Initially, they also train the beta, but they find if they fix the beta, they can like reduce inference cost and got relatively good samples. So they just fixed it.
So this one is a neural network.
The epsilon theta is a neural network.
And input is xt. So they use this one to predict x0.
The whole term here is used to predicting the x0. Just a second.
Oh, okay. One thing. So okay, this is the approximation of x0.
Yeah.
And then once you got this one, you still use this form, right? This mu hat, mu theta t is still this coefficient multiplied with x0, which is approximated by here, right? And
yes.
plus this one.
Yes.
My question is, why not they just model this one is just as neural network where the input is xt, perhaps including t.
Can you repeat that?
I mean, why not? Because we don't know x0. X0 is actually the image we want to generate finally, right? Eventually.
Yes.
So if I don't know x0, why not just model it as a neural network where the input is xt and also the time step t, something like that.
Yes, you can also actually the final form of the mean is essentially in this form, right? After me, like you can check the third term of the equation here. Sorry, I can't find my pointer.
Yeah.
Okay, here. This term is just in this form. It's a neural network with xt and t as the input. They just want to utilize the marginal conditional distribution and the conditional distribution in the reverse process. This can give some good formulation of the loss function, which you can see in the next slide.
I mean, in addition to that, what's the other benefit? I mean, they want to leverage this structure, right? So to me, it's I mean, if you just leverage if you just leverage this structure and then you construct or you predict x0 with your xt, right? And then I just feel it's not natural. Like if you can learn this, does that mean like, okay, given any xt, I can just use this form to predict x0, then that's done. I don't need to run a bunch of like.
Yeah, in their experiments, they also try to directly use the neural network to predict this term without formulate the mean in this ways. but the results shows that if they use this term, this kind of formulation, they can get better results.
So that means this structure has is useful.
Yes.
But what's the usage? What's the benefit? What's the rationality to approximate x0 in this way?
Actually, let's see there are try to all the way to this slides. Actually, if you have forward conditional distribution or transitional kernel like this, the inverse transitional kernel can be approximated by this term. Here we can here they just apply Taylor approximation and let fxk plus 1 equals to fxk, so they can get some kind of formulation in this way.
Doing this, you can using this, you can derive that form.
Yes, because the gradient of the log p k plus 1, if it's a Gaussian distribution, you can get some form of get the same form. I think they may get the same form as in the last slide.
Okay. In their paper, do they provide the justification?
Yes.
It's also based on Taylor expansion?
No, in this one, it's not. Because they just assume the simplest case with x0 is just.
I think it's from here, right?
Yeah.
You're assuming xt equals to like square root alpha t hat x0 plus square root 1 minus alpha t hat times some noise, right?
Yeah, they just combine these two structure together to predict the
from
reverse
this from the diffusion procedure, you can solve x0 in this form, and then they model the noise as a function of the state xt.
Yeah, the noise here can be treated as some direction from the forward process. They want to learn
that makes sense.
They just want to learn the direction from the forward process, and the revert it. They may get a reverse process as well.
Okay.
And here is the loss function, which is calculated as a cross entropy between the approximate distribution and the forward distribution.
Forward distribution is the generation of
the forward distribution. I mean, the forward distribution is the posterior distribution here, Q.
Is the way you generate is the way you diffuse the image or generate?
The forward is the diffusion forward. Here, the forward and the reverse means the diffusion forward and the reverse time.
Okay, I got confused again. So this one is the log marginal distribution of your image, right?
Yeah, P theta is the approximated like the generative model, and Q is the posterior distribution.
Posterior distribution of what?
Of the QX0 here.
QX0?
Yeah, QX0 is here is the true distribution of X0.
Oh, okay. 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 So P theta X0 is using your generative procedure, starting from Gaussian noise. You get the marginal distribution, right? And Q X0 is the ground truth distribution of those images.
Yeah.
Okay.
And the final loss function can be like can be treated as the sum of these three terms. The first one is a constant because xt is pxt here is a standard normal distribution, and as we can see in the previous slides, one t increases to t, the alpha term, the main term becomes 0, and the variance term becomes a identity matrix. So here is a constant. We don't have to calculate the first term LT. And here is
Isn't it because those alpha t's are just constant once you set up beta t's?
yes.
You don't care about that.
Yeah. Here we should know that the forward process is prescribed transition probability. So there is no parameters in the forward process we need to learn during the whole process. And here we can further formulate this KL divergence term into a weighted summation term here, which is the epsilon here is the noise happened in the forward process between adjacent time points, and epsilon theta is the epsilon theta here, which we use a neural network to learn the noise term in the forward process. And here, since the diffusion model is used for image generation, and X0 is a discrete random variable, actually. So they just construct a conditional probability of X0 based conditioning on a continuous variable, random variable X1 here. And the key term, the most important term in the loss function is the weighted summation.
So this one, this is a fixed, right? This is some constant distribution.
Yes.
This right from your previous. This is actually the forward, the diffusion procedure, and this one is a generation procedure, and you have your modeling of the noise at each step.
Yes, but in the training phase, we have to sample each intermediate xt based on the forward process.
Based on diffusion process.
Yes.
Okay. So so can you see it again? So this is from X1 to X0. This is still the last step of generation.
Yes.
So how do they define that? What does
because x0 is a discrete random variable, so they cannot simply calculate the log probability. So they just define some well-defined form, so they can
so what does D
do
mean?
the log probability more efficiently.
D is the dimension of x0 or
Yes, it should be.
and okay.
Because each element of x0 is a discrete value from 0 to 1.
So x here is the pixel of the image, right?
Yes. Each
Okay.
pixel value of
So
the image.
normalize in 0 and 1 or
Yes, because x1 is a continuous valued random variable. They just construct this conditional distribution.
oh, I see. This is an integral. Okay, so this is a probability.
Yes.
Okay, but if you consider like RGB model or RGB, it's not RGB images, just make grayscale images. You can still normalize the scale to be between 0 and 1, right? It should be continuous.
No. It's like 256 discrete values between 0 and 1.
Yeah, I mean I can divide them by 256, then it becomes a continuous value.
Yes.
Yeah, I don't know.
And the
Maybe
root-
Xin, you can comment on this.
Sorry. So your question is that for image, should we regard the image as a discrete function or continuous function?
Yeah, so the image, every pixel is an integer, right? Every pixel is a integer. Or if it's RGB, that means 3 channels.
Yes. It's in the range. Is in the range from 0 to 255.
Oh, I see. So it's actually a categorical distribution. Jun, is that right?
Yes.
It's trying to predict if the class 1, 2, 3, 4 to 256, something like that.
Yeah, because x0 is discrete, x1 is continuous. So they just construct this specific conditional distribution.
Yes, but I know, so for some other network like the UNet, it can also generate a different image from one image to another image. So for the output, actually, it can still be continuous, and then it do the quantization to make it to be integer. Yeah.
Yeah, that's what I thought initially, but it's fine. This is just you're sampling some categorical value at each pixel, and this is they use this one to define the probability.
Yes.
Okay.
And here we just noticed this weighted summation here with some specific weight, but in their experiments they find if they ignore the weights here and only update the unweighted term, they can get better sampling quality in image generation. And they for the backbone of approximation of epsilon theta, they use UNet, which is popularly used in image applications because it can extract more precise semantic segmentation. And in the most recent paper, in APES 2022, they found that UNet might just be the wavelets of the image.
Can you see again? UNet wavelets. Where do the wavelets come from, or where do you apply the wavelets?
Actually, you just wavelets just some like frequency transformation, like to extract the semantic meaning of the image. I didn't know too much about the wavelets on image applications, but here they can just give more precise semantic segmentation of the image.
So
Which
can you go back slide? Go back one slide more. Like
okay.
what does this sigma t square? Where does this sigma t square come from?
Sigma t square might let me see. Should be the sigma t square. Beta for sigma t. It might be the reverse process, the sigma theta here, because they fixed the reverse process variance.
Yeah, they use this one, right? They use this guy. Yeah, I just curious. It's fine. It's in their paper, right?
Yes.
I think this should be related to the beta theta t, something like that. Yeah, otherwise you don't use that, right? This one comes from the diffusion process, and this one is from the generation process, where your variance is there.
Sigma t, I think it must be the big sigma here.
But here in DDPM, you're actually fix this one to be beta.
Yeah, at each
beta
time
theta.
point, we just fixed it as the sigma t square times an identity matrix.
Oh, really?
Yes.
Shikai, maybe you can clarify. I think they're gonna use the same beta hat t, beta theta t.
Yeah, I think so. I think the sigma theta t, actually the notation is a parameterized. Actually, they just let this sigma theta equal to the beta t. So to make the diffusion term, they're exactly the same.
Actually, in this paper, they have different options for the sigma t here. Actually, it's not the beta t or tilde beta t. It's something bigger than the, I think, bigger than the beta tilde t. Yeah, they also mention it in another paper. Like here in this paper, they yeah, in this paper, they just try to approximate the reverse variance.
Also, they do some like interpolation, but the
Yeah.
problem is that why don't they just stick to the accurate beta hat? Accurate variance should be this guy, right?
These two beta can be obtained by setting x0 as a standard normal distribution or point mass. If x0 is just 1 point, you may get the reverse process variance as beta t. And if it's a normal distribution, you may get the variance as the beta tilde t. So that's why they interpolate these two values together to approximate the reverse.
So in that case, it's just a summarize, right? If you can only choose v equals to 1 or 0, right?
Yes.
Then
Here
what- I
the
mean,
v
that recovers
is learned during the training phase.
So, Jen, if you check the DPM paper, I think the section 3.2, maybe you can let me share my screen for very quickly.
Yes.
Oh, 1 second. Can you see my screen right now? I think there's a DPM paper, and you see right here. Just see set the sigma t equal to the beta t, or just set to the beta t hat. Beta t hat is the merge the all previous the noise step. I mean something like this one, and say both set and the constant, and just have the similar results. Yeah, right
Oh, so
here.
so this their generation procedure, they assume like each step the variance is just sigma t squared. You can choose it to be consistent with the exact derivation, which is beta tilde t, or you just set it to be beta t. It's that empirically they have the same
Yeah.
performance.
Yes.
And actually in their experiments, they try another theta t, which is bigger than both beta t here.
Okay, I may stop my share and let me turn to get it.
Okay. I'm sorry, we have to stop right now because I need to leave. We'll come back at 2:30, and yeah, and I think if you're not involved in this project, and if you have any other things to do, you don't need to join. I mean, you're welcome to join, but it's not obligatory. But I want Xin, I want Shibo, and I want Da and Shikai to join because your projects are related to this. Okay, let's continue discussion after 50 minutes.